Okay, I'm sorry for the slight delay. It's probably because my mind is eight years behind. So I'll get talking straight away. Let's see if this works. Yeah, it does. Fine. Okay, I'm going to very briefly describe a major revision of our 1998 database of Olivine crystal preferred orientation. Take you a few steps. Why would one want to build a database in the first place? And a few basics which I have to emphasize, because as technology changes, things get easier to measure, but you have to know how to measure it. Some of the objectives we have, and so forth. So, okay, why construct a database in the first place? It's a very time-consuming job, I can tell you. The first thing is, if you want to preserve your data, before you can preserve it, you've got to organize it in such a way that people can actually access it in a coherent manner. So the first thing you have to do is organize the data, standardize it in all sorts of ways. Then, obviously, you have to have it preserved on some sort of computer system, something that won't go out of date next year, because this is often the problem on long-term data storage. Then you can make an analysis of what I would call the ensemble of this database. In other words, you'd be looking for some sort of statistical trends that your data might have. So this is the power of a database. You can look at data, you can assess what is noise and what is really signal. And finally, if you're a good boy, you can share your data with other people. This is also important in today's world, and some of these databases will certainly become online eventually when they're in a condition which is easy to use. Okay, just a few remarks about some of the basics. The study of preferred orientation is a little bit of a sort of multidisciplinary, cross-disciplinary subject between earth sciences, material sciences, and so forth. Therefore, sometimes we don't get some of the basics in typical earth science training. And so I just want to emphasize something about what is traditionally called quantitative texture analysis. You can see those formula up there, but the first formula is quite important. We have delta V over V. This is describing what we call an orientation distribution function is, which is that function Fg. G stands for the orientation of the crystal. Okay? So it's effectively a volume fraction of the orientation space occupied by a given orientation. Okay? So that's quite a simple concept. But it is a volume fraction, and you have to bear in mind it has to be weighted correctly, otherwise what you do with it will not give you the right answer. So on the next line, we use a traditional normalization of the orientation distribution function so that if you have a perfectly uniform distribution, the value is 1. This is the same for pole figures. And the other important thing, if you want to measure a measure of the strength of the preferred orientation, you can use that formula on the bottom, so-called J index. It has other names as well. It could be called F2 and a texture index. So this is a simple integral of the square of the distribution function. So this is a measure, if you like, of the power. Oh, yes. Right. Now, this database we have originally was all constructed from data measured using a universal stage. So this was a very slow process. Our database from 1998 actually represents 25 years of measuring preferred orientation with a universal stage. So that type of measurement is rather slow. Maybe you get 100 points per day if you know what you're doing. You need to have a certain knowledge about optical properties to do this type of thing. This is now being generally replaced by electron backscattered diffraction, combined with an SEM, of course. This can be applied to any crystal system. This is often a highly automated process, therefore thinking goes out the window and data comes in. But you have to know how to filter this data, use this data. So the current speeds are anything from 30 points per second, I mean compared to 100 a day, this is pretty fast, to 1,000 points per second. Now most minerals you have to be working at the lower end of the speed scale, otherwise you'll have to do something like increase the beam current to a very high level, which will probably destroy your silicate mineral that you're interested in. But for metal it will work. Okay. So, measurement strategy. Okay, so this is just a simple numerical model I put together last night. So, typically, when we were doing U-stage measurements, we were doing one measurement per grain. Given that U-stage is extremely time-consuming, we'd measure somewhere in the middle of the grain the orientation, and the rest we would not measure. So this gives you a series of points, and each point corresponds to an orientation of the grain. Now that's valid if, in terms of quantitative texture analysis, if all the grains have the same size, or the same area, or the same volume. Otherwise, you're going to get a very strong bias because of the variation of grain size in your sample. And you have to be aware of this. So this 1 point per grain is not ideal for calculating things like physical properties, and should be avoided, in my opinion. The correct way to do it is to have a very fine grid. Then you can get the area weighting of all your grains, and you'll get the correct texture analysis result. Okay, the other way you can get properly weighted crystal preferred orientation is to use the traditional X-ray or neutron goniometry to get a volume area corrected preferred orientation data. The only problem with that is it is quite difficult to apply to polycrystalline, polyphase rocks in a general situation, whereas something like EBSD, everyone can find that in their university. It's easy to apply. You can use a traditional petrological thin section, etc., etc. But this is still good data. The other thing I put here, with no relation with the microstructure. This is often a great problem when people are using this high-tech beam technology. They don't actually look at the sample, which I regret. Okay, so once you have this type of data, of course, you can do all sorts of modeling. You can try and compensate from the fact that the sample you have is rather imperfect representation of the in situ material, and so forth. Okay, so that's more or less the same thing. Typically, the problem is you'll have things like decompression microcracks in your sample, and even a physical measurement is not actually going to give you the in situ velocity. Okay, here we go with the database. Okay, in 1998, all U-stage data, and what I plotted here is fabric strength against seismic anisotropy, either P waves or S waves. You'll see the two scattered data. There's only 110 samples in this particular database at that time. You'll see there's a nonlinear relationship between fabric strength and anisotropy. This was for applications like this, trying to understand about seismic properties below the African craton, using samples which are located in depth by using the petrological paleobarometry and temperature determinations. Okay, so in 2000, the database looked a bit more like this, which allows me to emphasize that Olivine has this very non-linear relationship with fabric strength. Orthoperoxy, it's not very well defined because there are relatively few data points, but you can see it behaves completely different because the relationship between the preferred orientation and the elastic anisotropy of the mineral is not the same in Olivine and orthoperoxy, despite the fact that orthoperoxy is as anisotropic as Olivine. Okay? It's all to do with the relationship between what is the preferred orientation and what is the single crystal elastic anisotropy. Okay. So, in 2001, Shunkarato and his colleagues came up with a new classification, which we all use more or less these days, for these fabric types. And so this comes from my 2007 book chapter, where you can see the relationship between water content, stress, and these various fabric types. However, I'd like to point out that a lot of the data, if I can press this, a lot of the data we have is often like this. It's not exactly one of these fabrics, ideal end member fabrics. So there's quite a lot of transitional nature in these preferred orientations, which is not represented by a certain number of limited end types, if you like. Okay, where does the data come from? Well, it comes from more or less all over the place. I haven't put absolutely everything there, but we have a very wide range of geodynamic environments in this database. Okay, how about visualizing some of this data now? Okay, now this is a database, now has 605 samples, so we've gone up quite a lot. It's not an order of magnitude, but it's gone up quite a lot. It's 6 times the original. You can see there's a much more scatter now, but the clouds are looking much more dense, and we could probably start putting trend lines through that if we wanted to. So this first one, I'm using that J-index of the ODF against the seismic anisotropy, just like we did in the original paper. Now, you can also use things like the misorientation distribution functions J-index in the same way, and you'll see that the shape of these relationships is somewhat different. And then finally, well, not quite finally, but nearly finally, I've used the equivalent of the M-index introduced by Peter Skimmer a few years ago, and you'll see this gives a similar type of trend. The trends are not exactly the same in each case. Each parameter gives a slightly different representation. One can also use as a metric the pole figure J-index, and this is the one for the A-axis, the B-axis, and the C-axis. You'll notice that the A-axis looks quite similar to the other indices that we've used, whereas in particular, I can get hold of it, the C-axis is very different, and in fact it hardly varies as a function of the fabric strength. The reason for this is a lot of the fabrics in this database are this so-called A-type, the more common. Okay, so then I wanted to test whether I could do a forward model to show that, in fact, the database is mainly A-type. So I did some Vpsc modeling of these end-member fabrics. So you can see the variation as a function of seismic anisotropy. You'll see all the ones with an A-axis glide system, if you interpret these fabrics, are red, and the ones with a C-axis glide direction with blue, for obvious reasons. So if you then superpose that through onto the database, which are the green points here, you'll see that these end-member fabrics more or less encompass the spread of the data that we have. Okay, how am I doing for time? 1 minute? 1 minute. Okay, so this is one of these fabrics which would not fit in the classification. Some of the dispersion of the preferred orientation in the database, in the scatter, is undoubtedly due to the presence of recrystallization. This is porphyroclasts here. These are the recrystallized grains here. You can see there's much more dispersion in the recrystallized grains. Plug. This is a free open source texture analysis lab Toolbox, which we've been developing with my colleagues in Germany, which is free. You can download it. And you can do all these calculations I'm showing you have been done with Mtext today. Just give you an idea, this one line will allow you to draw these 3 pole figures. This one line will allow you to get the Voigt-Royce-Hill averages of your sample. It's a very condensed way of working. Okay, we're also constructing other databases. Won't go too much into this. Some of this will be pumped into the material properties open source database. I'll have my own database, but we'll put it in several different places. We talked to Jay Bass about putting it on the Compress site as well. So we're busily constructing these new databases, and my last plug is if you have any new single crystal elastic tensor data, it's the time to send me a PDF. Right. So I'll just conclude with that, and I'll leave it up.
Thank you. One very quick question, maybe. We don't see that much from here.
Are they still there?
Yeah, this is here. Okay, so then we'll move to the next. Thank you. So we move to the next talk by Yannick Ingrin, entitled Hydrogen Defect in Forsterite and Olivine, a Critical Review.
Okay. Good morning, everybody. Okay, you will see immediately when in my talk I disagree a bit with the talk of Dave Colted just before. But what's good is that I'm sure in the future we'll converge in a full understanding of the defect of water in olivine. So in this talk I will focus mostly on forsterite. But you will see that the application to olivine is obvious. Okay, I re-ask what Dave said just before, the importance to know what the nature of defect in olivine, because it's what control the solubility, what control the partition coefficient between, for instance, pyroxenes and olivine in the mantle, and which is very important also, it's control the physical properties. For instance, the one type of defects can affect the deformation, while another one cannot. Okay, in this slide, I show you a OH spectrum of forsterite doped at 2 GPa, it's not 12, 2 GPa for 1400 degrees C, and the spectrum was collected at close to the nitrogen temperature. And what is very interesting is that this particular sample, you can find almost all the type of OH band you have in forsterite. It's a lot, it's 24. But what I would like you to concentrate in, as Dave showed, we have mainly two windows, frequency window, where we have the main OH bands. This high frequency window here, and a low frequency window here. And the interpretation of this two type of spectra has been demonstrated and shown from the ab initio modeling. A lot of simulation have been done, and here I show the two most recent by Ballan et al. 2011 and Yumemoto et al. 2011. And you see that Dave showed it already, but when you try to modelize a defect with where you replace the magnesium by 2 hydrogen, you only have 2 bands for M1 defect, 2 bands for M2 defects, and with the bands very close in frequency. And the only way to simulate the spectra, you get bands around 3,200 at low frequency. This study shows also that there is many configuration for the substitution of silicon by 4 hydrogen, and all them show at least 4 bands. They show 4 bands for each type of defects, and they are all in the high frequency, between 3,400 and 3,700 centimeter minus 1. So from the point of view of the modeling, ab initio modeling, you have no way with this sample type of defect to get bands in this area. And you have no way from this sample type of defect to get more than 2 bands. You have no way to get 4 bands. You cannot justify this. Okay, why we have this different behavior in terms of frequency between the substitution of hydrogen to silicon and the substitution of hydrogen to magnesium. This is a simulation and modeling made by Verma and Karki. They show that when you create a magnesium vacancy, you have a relaxation with a small shift of the oxygen, the neighborhood oxygen, by only 7%. So you enlarge the site, but there is from a small proportion. By the opposite, when you create a silicon vacancy, remove a silicon, you have a strong shift, a big relaxation of the tetrahedra by more than 35%. It means that when you have a vacancy, you have a huge distance between the oxygen in the tetrahedra, while in the empty octahedra, the distance between oxygen is smaller. It's why you have, in this case, a stronger H bond and then a lower frequency of vibration of OH, while in the silicon vacancy replaced by hydrogen, you have a weaker H bond and a stronger vibration frequency for the OH. We did also, in this sample, we did a measurement of the evolution of the bands with the temperature from minus 194 to 200 degrees C. And what is interesting is that in this area of high frequency, the bands are very narrow. They shift only a few centimeters minus 1, and they have almost all the same behavior. At the opposite, in the area where we have these 3 bands visible, they are very broad, and they shift a lot with the temperature. That they have completely different behavior. If I come back here, I said they are very narrow and so on, except 2 bands. There is here one band around 3,600 that shift with temperature to 2,624, and another band here around 3,550. These 2 bands, you can see on this diagram, they shift a lot. They are different of the other one. We don't know what are these defects, but they are different from the one we have here, which we think are linked to silicon vacancy. Okay, forget this one, but remember this one at 3,550, because we'll see it again in the next slide. This is, here I show you some of the experiments result of hydrogen solubility in forsterite, and here one in olivine. But there is many other ones I didn't represent here, but they show the same behavior all. We always find in forsterite these 4 bands, narrow bands at 3,612, 3,566, 3,578, 3,480, which we think are linked to silicon vacancy. And we also find this fat band always oriented, polarized along B. In all experiments, even in olivine, you can find it here. And this is the defect I call H3, which I don't know yet the nature. So what's important, you saw also that all these, except this one, which has less magnesium. All these spectra, and they don't have any bands at low frequency that could be related to magnesium vacancy. So the important point is that even for forsterite, for olivine it's a bit more complex because you have even more bands, but for forsterite you can see that in all these experiments we find something like a combination of 75% of the surface of the band is linked to the band. The 4 bands here we think are linked to silicon vacancy, and 25% to these H3 bands, which we don't know what's the origin. But okay, it's a single band. Something also interesting. It means that we have no way to modelize the solubility. If you take all the absorbance of the band, you have no way to modelize your solubility by a single law like this. Because these 2 defects, the H3 and the one related to silicon vacancy, they are their own fugacity exponent and their own activation volume. So you cannot do it. And the most difficult things when you try to plot and to fit this law is that the water fugacity is depending on the pressure, and so you have to fit 2 parameters at the same time, and most of the time you can fit the data with an infinite couple of n exponent and delta V value. Well, but recently, Sean Carato did a very interesting experiment. He buffered the water content and did experiment at constant pressure. This is the result he got. This is the pressure was 5 GPa, and you see the evolution with spectra for the water fugacity. And he plotted the total absorbance of the band, and he found an fugacity exponent of 1. But he also noticed that, you see, the spectra are quite complex, and he noticed also that the band, I put this one, I put a cycle on the band that we think are linked to 4HSI, and this specific band, you can see, they evolve much more faster than, for instance, this band at 3,600, we don't know what it is, which is very high compared to the band here at 3,612. So it means that if all the absorbance has an exponent of n equal 1, some of the bands have a different exponent. It justifies the fact that we have here several types of defect. It's not a single defect. It's not a magnesium defect, but it's not only 4HSI defect, but it's 4HSI defect plus this one and plus some other one, because in the case of olivine it's more complex. So, in summary, what I would like you to remember, okay, I disagree with the fact that all the solubility is controlled by 2H-Mg. It's not possible in terms of spectroscopy, in terms of modeling of defects. You have too many bands. You cannot fit with one single defect like that. So we think that for forsterite, the solubility is controlled by one defect of this type, plus an unknown defect here that represents something like 25% of the concentration. But what I would like you to remember after this talk is that there is no physical meaning to fit with a single law, because it's a combination of several defects with different n value and with different delta V value. That's all. Thank you.
Questions or comments? I don't see any.
Sean.
Please, yes. Sean?
Regarding the silicon process discussion,
Yeah, it's a difficult question because you know that it's difficult to realize high temperature spectra, and your bands will become so broad that you cannot see anything. But it's okay. I will not reply to the question, but it's true that all the modeling, the numerical modeling, are done at 0K also. Yeah. So, but I think there is several defects. It's sure.
Okay, thank you. We move to the next talk.
Next talk. Next speaker is Dr. Glenn Gaetani, and title is Hydration of Mantle Olivine under Variable Water and Oxygen Fugacity Condition, and combined SIMS and FTIR study. Thank you, please.
Okay, thank you. So those first two talks, or those last two talks, set up my talk very nicely. I'm not going to try to convince you about where the hydrogen is, but I want to show you some new experimental results on hydration of mantle olivine, and we combined data from SIMS and FTIR. So for the SIMS data, we used that to get the total water, and then for the FTIR, we looked at the point defect populations. So as previous speakers have pointed out, small amounts of water dissolved in anomalously anhydrous minerals strongly affect mantle rheology and also the melting point of the upper mantle. And olivine represents about 70% of the mode of a fertile peridotite, and it's an important host for hydrogen in peridotite. What I want to talk to you about today are solubility experiments that we analyzed by both SIMS and FTIR to investigate the influence of different thermodynamic variables on hydrogen solubility in olivine. And two of the things that we found is that the influence of oxygen fugacity and forsterite content in our experiments on water solubility is weaker than had been inferred from previous studies. So we did experiments that are a bit different from what are typically done. We measured water solubility using large single crystals of San Carlos olivine. And we did experiments at 1, 1.5, and 2 GPa, and it was surprising to me that there's actually been a big gap in the data between the 300 MPa that a lot of the work in Dave Kolstedt's group's been done at, and 2 GPa. So there's basically nothing in there. So we filled that in a bit. Oxygen fugacity was buffered at the iron wistite, magnetite, and nickel-nickel oxide buffers. We also used mixed volatiles, mixing water and CO2 to explore the low water fugacity region. And the run products were analyzed by electron microprobe for the major elements and by SIMS for total water. And then a subset of the samples were analyzed by FTIR to look at the point defect populations. So this is how we did the experiments. We took large single crystals of San Carlos olivine, and we made capsules out of them. So this is essentially a liner that goes inside a nickel metal capsule, and the buffer goes in the bottom between the San Carlos olivine and the nickel metal. And in the case of iron wistite, this was replaced with an iron capsule. And then we put some water in a hole in the center that cord from the center of the San Carlos olivine, and this allowed us to definitively say that there was water present at the end of the experiment because either there was a void space in the center or there wasn't. Okay, so that was pretty definitive. We did a time series to see how long it took to equilibrate with this sort of an experimental setup. So we did experiments at 1 hour, 6 hours, I believe that's 12 hours and 24 hours. And you see that in the 1 hour experiment, water was very heterogeneous. And the concentration, or the hydroxyls were very heterogeneous, and the concentration was different from what we saw in the longer duration runs. But it looks like after about 6 hours with this sort of a setup, we're getting a constant hydroxyl concentration. And this is actually an experiment in which we took the San Carlos olivine and put it in a 1 atmosphere furnace to pre-equilibrate the defect population at nickel-nickel oxide. And you can see there's very little difference in the hydroxyl concentration between that and one that was done without pre-equilibration. So in the next few slides, I'm going to show you two things. On the left, I'm going to show you the raw data, and on the right, I'm going to show you the data that were fitted to the solubility equation, and then holding all the variables except the one on the x-axis constant. So here is a plot of log of water fugacity versus hydroxyl concentration in ppm, and you can see that there's a strong positive correlation between water fugacity and hydroxyl concentration. That's what we expect from all the previous work. And when you hold oxygen fugacity, pressure, aluminum concentration, and forsterite concentration constant, that correlation gets even better. So these are all data corrected for constant values of these variables. If you look at oxygen fugacity, you see that there's essentially no correlation in the raw data between oxygen fugacity and the hydroxyl concentration. But if we then take the fit to the solubility equation, you see that there is a positive correlation when you hold all the other variables constant. So most of this scatter is because of the other variables, and that's should be obvious just from looking at the nickel-nickel oxide data, where you have a wider, span the entire range of hydroxyl concentrations. But so what this implies is that if you go from iron wustite to a nickel-nickel oxide, you increase the hydroxyl concentration by about 50%. So that's smaller than the values that Grant and all inferred. And what this would mean is that at the range of upper mantle oxygen fugacities, this is a relatively small effect. Pressure, if you look at the raw data, there appears to be a positive correlation between pressure and water concentration, but this is mostly a artifact of the positive correlation between water fugacity and pressure. And when you hold the other variables constant and just look at pressure, you get a negative pressure dependence, which is what you expect, and we get a delta V for hydrogen incorporation of 5 plus or minus 2 times 10 to the minus 6 meters cubed per mole. So that's in the range of what other people have gotten. The biggest surprise for me was when we looked at aluminum concentration. I had expected going into this that we would find a positive correlation between aluminum concentration and hydroxyl in the olivine. The idea being that you put some aluminum in a tetrahedral site and you charge balance it by a proton, so the more aluminum you have in that tetrahedral site, the higher the concentration of hydroxyl. And what we found is actually the opposite. And you can see there's a negative correlation in the raw data, and when you hold all the other variables constant, you see the correlation gets very strong. And what we think is going on here is the fact that that aluminum defect with aluminum and octahedral coordination charge balanced by a proton is an extrinsic defect. And I think what's going on is in that these experiments you're only really equilibrating the intrinsic defects. You're not equilibrating the extrinsic defects. And so what we're actually seeing here is a reflection of silica activity. So as you increase silica activity in the system, you decrease the aluminum concentration in tetrahedral coordination, and that's why you get this negative correlation. The other thing that surprised me in the data was the results for forsterite content. So we've got forsterite content varying from about Fo88 to about Fo92, and in the raw data, there's a negative correlation between forsterite content and hydroxyl concentration, but when you fit it to the solubility equation, you find that there's no statistically significant forsterite term in there. And that holding all the other variables constant gives you a constant hydroxyl concentration, and we see no dependence, at least at these conditions and over this forsterite range, on the forsterite content. So here's some FTIR results. This is holding oxygen fugacity constant at nickel-nickel oxide and varying water fugacity. So we start at the lowest water fugacity in the mixed volatile experiment with 0.52 GPa increase, and you see mostly these high wave number peaks that were shown in previous talks, and very little at the lower wave numbers. But as you increase the water fugacity, you see that these low wave number peaks get really big really fast. And in fact, if you do an integration and have the dividing line at 3,400, these peaks are actually dominating the water concentration. It's a similar picture for oxygen fugacity. So this is now at a constant water fugacity of 4.65 GPa. The oxygen fugacity of the Worcestite magnetite buffer is shown in green, and you can see that it's dominated by these higher wave number absorption bands. But you do see something at the lower wave numbers. But as you increase the oxygen fugacity from Worcestite magnetite to nickel-nickel oxide, these lower wave number bands get really big really fast. So to sum up, water fugacity is the most important variable controlling hydrogen solubility in olivine. That shouldn't be a surprise. Water solubility increases only by about 50% between the iron Worcestite and nickel-nickel oxide buffers, so that's a relatively small effect. We see no dependence in our data on either the forsterite content. So this is at 1 to 2 GPa and forsterite 88 to forsterite 92 olivines. We see evidence that, and it makes sense, that we're only equilibrating the intrinsic point defects in these types of experiments and not the extrinsic point defects. And in order to do that, you really need to do a sort of a synthesis experiment where you grow the olivine from a melt. And the low wave number or group 2 absorption bands that people discussed in earlier talks are sensitive to both water fugacity and oxygen fugacity. And as you go from low values to high values, they get really big really fast. Thank you.
Thank you very much. Now open for questions, comments. Please.
This big band at 3,350, it has been suggested it's related to aluminum. Could you correlate this?
We don't have enough FTIR data. We just did FTIR on about 5 samples, and there's not enough variability in the aluminum to see if it correlates. They're all at around 200 ppm aluminum.
No question? Please.
Can you just briefly tell us a little bit more about the FTIRs when they're unpolarized?
No, they were polarized. They were polarized on 3 orthogonal directions parallel to the crystallographic axes, and those were total absorbance spectra. And if you want more detail than that, I'm afraid you're going to have to ask Ken. He's my expert.
Okay.
Okay, thank you.
So let's move on to the next talk. The next speaker is Olivine, and the title is Water Retention and Rheology of Titanium Doped Synthetic Olivine.
Thank you. Thank you very much. So following on another experimental talk, trying to contrast the experiments or balance the experiments a little bit with the theoretical talks. So in particular, I want to focus on the titanium-doped synthetic olivines. And by background, this was published in 2007. The rheology of synthetic olivine, forsterite 90 olivine, that contains no trace elements, and to our surprise at that time was very strong. And subsequently, we have argued that the difference here between the published rheology, 2 orders of magnitude weaker, and what we found for the very fine-grained aggregates is due to the presence of some melt contents in these samples, which has been confirmed to some degree by theoretical models by Takai and Holtzman that essentially say that, yeah, at very small melt fraction between 0 and 1%, there's a dramatic weakening of the rheology due to melt. But they, in their calculations, only got about 1 order of magnitude or so, whereas what we're seeing here is more than that. So we started thinking about trying to, in particular, look at trace element, because the suggestion was that since these are trace element free experiments, that trace elements can modify the rheology of these synthetic samples relative to natural olivine. What we started doing with is adding calcium to these samples, and we found essentially no difference, and that's also confirmed by work in Dave Kolstad's group, that addition of calcium or other trace elements does not enhance the rheology. So that cannot explain the difference here in this 2 orders of magnitude. More interesting, though, when we stumbled across titanium, when we started adding titanium, this is when really large differences in the rheology started to emerge. So I'll focus on the titanium work in the rest of the talk. Again, some background discussing these Fourier transform infrared spectra. There's work in titanium. This is another reason why we started looking at titanium, because there's at least some work that shows that titanium is very important for water incorporation in olivine. So at the top is a spectrum from San Carlos olivine, and the important absorption bands here are at 3575 and 3525. Those are the 2 dominant peaks in this is a natural sample, San Carlos olivine. And I'll come back to this. This is really the key point I want to make, the comparison between natural samples and the experimental spectrum. So in this paper from Berry et al. In 2005, they did all sorts of experiments trying to reproduce these natural spectra, buffering different oxygen fugacities. And what they found was that they can only reproduce these natural spectra if they buffer their samples with rutile. So these are piston cylinder experiments where, in addition to, so here's forsterite 100, FO90, OPX, and then in both cases rutile, and only with rutile present could they produce those 2 bands. So they argued that this defect that they're seeing is a titanium clinahumite-like point defect. So the titanium clinahumite has, the actual mineral has an additional band, but in the olivine, only 2 of those titanium clinahumite bands are present. Those are those 2, and I'll emphasize those 2. And they did further work. They looked at the spectra, or they looked at these samples with xanes, looked at titanium coordination in the synchrotron, noticed that on hydration, the synchrotron seems to change its coordination environment, which they saw as confirmation of this particular point defect. And also theoretical work by Andrew Walker and others found that the titanium clinahumite type point defect has the lowest energy of the available defect sites, and I'll come back to that. So I want to emphasize natural samples, and one aspect to consider here is the absorbance normalized, in this case, I think to 1 millimeter. It's written here. And these are natural samples from a range of settings. This is another paper here. The dominant bands in all of these are these 2, 3575 and 3525. These absorption bands that are consistent with this titanium clinahumite-like point defects. This is what you observe in all of these natural samples, and these are mostly spinel peridotite xenolith. I think here's an example from a paper by Peslier et al. In garnet peridotites. Again, while the spectra are a little bit more complicated, again, the dominant bands, absorption bands, are those 2 indicated by those 2 lines. So the question then is, how does this relate to the experiments? And I've contrasted the 2 here. I'm sorry, the reference here should be 1996, I think. I'm getting a little bit ahead. But the key part is the absorbance. So the xenolith, this is one from the Bell et al., at 1 millimeter thickness, as here, normalized to 1 millimeter thickness, is that this contains much less water than the experimental samples. And as Glenn just outlined, experimentally, the experimentalists are generally very careful to make sure that the samples are water saturated by, for example, puncturing the capsule, making sure that there's some water emerging. That is, the water contents in these experiments are water buffered, water saturated. So it is possible to hydrate a variety of defects, and that's what you see in these much more complicated spectra, that is not only one defect that's hydrated, but a range of defects. Whereas at very water undersaturated conditions in these relatively water poor samples, and before from the study by Bell et al., some of the absorbances only went up to 0.5 or so. At very water poor conditions, apparently what's hydrated first is this titanium clinahumite point defect. So that appears to be the most stable defect that's getting hydrated first. And then when there's a lot of water available, you hydrate additional defects, which then have, of course, different dependencies to changing the environment. So the experiments that we're doing then are not water saturated, so we're not buffering. So the experiments here in a Patterson rig, we're not buffering. In fact, we're not even adding water. This was the other surprise. We're not even adding water to these samples. So jackets, and this is important, the jackets plus liners, so the sample is in contact with the liners, not directly with the iron jacket. No buffer, and as I said, we don't, except for one sample, we don't add water. So surprisingly, some of the spectra, and you can see that they're also relatively complicated, we did experiments, obviously, with undoped samples. These are the ones where I showed the rheology that were very strong, so certainly we didn't have any water in those. The problem was to explain why they're so strong. And the spectra that we get from those are down here, the red ones, showing consistent with the rheology that these are really dry. And we've done many of those experiments with exactly that setup, iron nickel liners and the samples encapsulated in the Patterson rig. When we started doping these samples with titanium, we saw very different behavior, and we saw notably very different water contents. So the drying process for all of these samples is exactly the same. The samples are, before hot pressing, fired several times. They're hot pressed in this iron nickel liner. Precision ground, again fired before deformation. I showed some of the rheology later on. So we're trying to keep these samples as dry as possible, and it works for these samples down here. When we add titanium, it doesn't work anymore. All of a sudden, in these samples that should really be dry, we're getting significant amounts of water. And that there's some range in here. This is one sample where we don't really know why we have quite as much water in these iron nickel liners. Certainly when we have, so these are 0.1 weight percent titanium, a bit high relative to natural samples. If we look at 0.02 weight percent titanium doped samples in iron nickel liner, these essentially after hot pressing also are dry. A key point is already at 0.1 weight percent, the two peaks that are emerging out of this very broad absorption region, which makes quantification of water content a little difficult in these samples, again, are those two related to the titanium clinahumite defect. So here's one sample where we actually added water deliberately, so we added a quantity of water. None of the other samples were water added. We get a very different, so this is undoped, there's no titanium there, and we, in fact, we get one sort of absorption band at much smaller wave numbers. So very different infrared spectrum already for the undoped samples. The bigger surprise then was when we, instead of using iron nickel liners, we used platinum capsules. And here the absorbance, these are unbuffered, undoped samples, so no water added. So unbuffered, no water added samples. And we get absorbances that are comparable to those natural samples. And the dominant peaks very clearly here are related to the titanium clinahumite type defect. And we tried various, because this was such a surprise, we repeated that over and over again, it seemed like. Also with different capsule material, so gold, palladium, we get the same results. So as long as we're in platinum capsule, the same material, so the 0.02 weight percent titanium, which on the previous slide essentially was dry, when we put that in platinum, we can actually find that we have significant amount of water in these samples. And again, these samples are dried, fired at 1400 degrees C overnight for more than 12 hours repeatedly. So what is then the effect of this defect on the rheology of these samples with this water content? The other point I wanted to mention is that we get in these platinum capsules, we get an inverted water gradient. Inverted is because we actually have more water at the edges of the sample relative to the sample interior. So if you look through these, more water at the edge. So we're not losing water, or we're not losing water very fast. We're actually retaining significant amounts of water. The rheology then, relatively fine-grained sample with 15 micron mean grain size. So here's again the rheology of the dry, fine-grained, undoped samples relative to the rheology published by Hirth and Kolstad in 2003. You can see that a significant portion of this difference is made up. So these samples have become much weaker. while containing a relative, so this is the blue dashed curve here, this particular sample, while containing relatively small amounts of water. And possibly, during the experiments, we're not buffering the water content, we also are losing some of the water. But the rheology with titanium and some water present in this broad absorption region, intermediate between those two. So in diffusion creep, certainly we see a substantial enhancement of the strain rates. Then the other part was we know that we have water in the samples without even looking at them, because the samples that are titanium doped are much more coarse grained. One other aspect of the undoped sol gel samples was that they remained very fine grained even at high temperatures. These one here, we have substantial grain growth, and this sample was deformed to only about 20% strain or so in compression, but you can see it was very coarse grained and has substantial amount of recrystallization. So certainly deformation in the dislocation creep. And I'll show the rheology for this sample. So here's at 1300 degrees C, samples deformed in platinum and in iron nickel. Here's the dry diffusion and then dislocation creep rheology of Firth and Kolstad. This sample here has a relatively low water content, so probably 10 ppm or so or less. And it's somewhat weaker than the dry rheology, somewhat stronger than, this is Chopra and Patterson, 1984, Anita Bay Dunite. The sample in platinum with 0.028% titanium is significantly weaker and has a normal power law creep rheology with an exponent in this particular case just fitted to these data of 3.2. So we've done a couple more experiments to confirm this. So this was the higher temperature, 1300 degree data, and this is at 1200 degrees. Again, in iron nickel liners, very little retained water. Then here in these platinum capsules, more retained water. The water contents, so the curves here calculated from the Hirth and Kolstad rheology, the curves, of course, are made to coincide. So I used a water content of 400 hydrogen per 10 to the 6 silicon. The water content in this sample is probably higher than that. This was just for reference, so the water content here is probably more like 600 or 700 or possibly 800. We have to figure out how exactly we integrate the FTIR spectra. But higher water content than this, whereas conversely here, we probably have a lower water content, but the samples are weaker. So there's trade-offs probably with the activation energy. The point is, though, that in platinum, without adding water, but having titanium-doped samples, we have a relatively weak rheology that corresponds to the rheology of samples that were water buffered. So the important part is, as far as we are concerned, is that the titanium is probably the crucial part. So looking at that titanium-related defect, titanium clinahumite defect, gives us spectra that are comparable with natural samples and appears to be the dominant defect that we need for water weakening in the olivine. Thank you.
Thank you. One quick question.
How much titanium is actually in your sample?
We have done some microprobe work. It's roughly consistent with what we put in. So when we do some, when we analyze those, we get roughly 0.028% or so.
Okay, thank you. So next speaker is Dr. Mormont, and the title is Incompatible trace element in olivine using scandium, yttrium, vanadium as temperature and redox monitors in basaltic magmas. Thank you.
Right. So we've been doing a lot of experiments looking at the controls on trace element partitioning between olivine and silicate melt. And we try our best with these experiments to isolate the variables one at a time. So we've been able to get some interesting results for the effect of melt composition, olivine composition, and temperature, but for a range of trace elements in olivine. But of course, it would be very difficult to show all of that in less than 15 minutes. So today I'm going to focus on three key elements: vanadium, scandium, and yttrium. and hopefully illustrate to you how the partitioning of these trace elements in olivine can help us to reveal oxygen fugacity conditions and temperature in basaltic rocks. So motivation for this study is the current debate about the oxidation state of terrestrial basalts and their mantle sources. And one view is that the redox state of iron in basalts retain the memory of the mantle source, and therefore the subarc mantle is more oxidized than the ambient mantle below mid-ocean ridges. And the key argument for this observation is that we see a positive correlation between the ferric to ferrous iron ratios in basalts as a function of proxies for the addition of slab components, like, for example, water and also barium over lanthanum. Of course, as you can see here, primitive arc basalts plot on this side of the array and morbs on the other side. The alternative view is that the oxidation state of iron in arc basalts only become more oxidized at shallow crustal levels. And the argument for that is that when you look at ratios of trace elements in basalts, which have a very similar geochemical behavior, but one is redox variable and the other is not. For example, vanadium is scandu, but also you can see that on zinc over iron, there is absolutely no difference in these ratios for morbs and for primitive arc basalts. Problem is that even for morbs, there is some uncertainty in the actual ferric to ferrous iron ratios. As you can see here, for example, these are more recent wet chemical data by Bezos and Hamler for mid-ocean ridge basalt glasses, and they are relatively more oxidized than the results previously obtained by Christie. And if you go to more recent results by iron zanes, it seems like the ferric to ferrous iron ratio is actually even higher. One of the problems in interpreting these results is that there are several potential reactions that can change the oxidation state of iron in silicate glasses. And I'm just going to focus here on this one, which is basically sulfur and iron. If you see here, like the two sulfur species that we typically find in silicate melts, sulfide and sulfate, there is an 8-electron reaction. So sulfur has a very strong redox potential, which means that even tiny amounts in silicate glasses might be able to change the oxidation state of iron significantly. These types of interactions between sulfur and iron might happen either in the form of electron exchange reactions or charge transfer reactions on quenching, because these types of reactions tend to be temperature sensitive, or they can be due to degassing of sulfur, SO2. So clearly, alternative ways of estimating the oxidation state of basalts would be welcome, and olivine is the first silicate phase to crystallize from primitive basaltic liquids on cooling. It is also a liquidous phase in virtually all types of planetary basalts. It has a relatively simple crystal chemistry. So the trace element partitioning relations preserved in olivine phenocrysts may give us a better idea of the pre-eruptive redox conditions of basalts, especially because they should not, in principle, be affected by late-stage degassing or charge transfer reactions on quenching. So among the redox variable trace elements in olivine, vanadium is definitely the one that shows the strongest sensitivity to oxygen fugacity because it can happen in 4 different oxidation states, and basically vanadium 2+ is compatible in olivine, but vanadium 5+ is highly incompatible, so the bulk partitioning of vanadium in olivine varies by a factor by 4 orders of magnitude. Of course, other variables will affect the partitioning of vanadium, like, for example, melt composition, olivine composition, and temperature. So previous calibrations of this relationship are only of limited application because they did not address these effects. So we basically did some 87 extra partitioning experiments over a range of compositions, temperatures, and oxygen fugacity, and which combined with previous results would make some 889 partitioning data, and these results will be soon to be published in Journal of Petrology if anyone is interested. So looking at all of these results, we were able to derive an expression which relates the partition coefficient of vanadium to relative oxygen fugacity, and also account for the effects of composition of olivine, melt composition, and also temperature. So this is just a plot showing the measured partition coefficients for vanadium and the ones calculating using this expression for the experimental results. And this is a plot showing the FO2 of the experiments against the calculated FO2 using against this expression. So if you look at the root mean square deviation for these results, we will get an estimate of the precision of this oxybarometer, which is about 0.24 log units. Of course, if you want to apply this vanadium oxybarometer, we will need to know temperature, and we could do that using traditional MgO gel thermometers, but we thought it would be a good idea to also get temperature information from trace elements in olivine, and it turns out that the rare earths are quite useful to do that because they substitute into olivine in a similar way, but they tend to show kind of a different temperature sensitive. So, for example, looking here at the electric strain parameter of this blending wood equation with data fitted here, you will see that there's a temperature correlation. So basically any exchange partitioning between one element plotting here and one element plotting here will be temperature sensitive, and we've chosen scandium and yttrium because these elements have some higher concentrations in natural olivines, which make the gel thermometer more sensitive and more precise. This is just to show that the effect of composition on the partitioning of rare earths in olivine also may be significant, but they tend to have the same magnitude. So if you're doing KDs, if you take the KDs, this should more or less cancel out. So this is the same way what we were able to get with these experiments. We can relate the KD scandium yttrium to temperature and account for the effects of pressure, composition of the olivine, and also the melt composition. This is just a plot showing the KDs calculated versus the one measures here. And this is the thermometer. And we get, again, using the root mean square deviation, an indication that the precision about 15 degrees. Well, this plot is just to show a comparison between temperature calculated for using a range of MgO gel thermometers, and want to point out that essentially this is a subset of the experiments we selected to avoid any far from natural composition. But basically we get again 15 degrees time in precision, but the other gel thermometer is about 25. So it's slightly better actually. Okay, I still have a few minutes. I want to show an example of the application of this oxybarometer in gel thermometer to natural olivines, and looking at mid-ocean ridge basalts, which are quench samples, which has some nice microphenocrysts of olivine. I should point out that these olivines are fairly homogeneous, as you can see here in this iron elemental map. Here, this is iron-magnesium ratio, so they're fairly homogeneous crystals. And temperature-wise, the iron-magnesium KD are in relatively good agreement with what we get from traditional MgO gel thermometers for MORBs. But when we look at the oxygen fugacity calculated using the partitioning of vanadium, we see some half a log unit more oxidizing conditions if we compare with the iron Zane's results of Cottrell and Kelly, which are here transformed into relative oxygen fugacity using the Crescent-Carmichael relationship. This difference would mean basically going from a fraction of ferric iron of 0.16 to 0.19. We're not sure exactly what this difference actually means, but as you can see here, there is both data sets have show a correlation between the magnesium in the melt as a function of relative oxygen fugacity. This is a rough negative correlation here as well. So this is compatible with olivine fractionation, although these slopes appear to be different. And although we see in our results that the magnesium in the melt correlates with sulfur, we don't see any correlation of sulfur with the actual relative oxygen fugacities. So clearly there's work to be done here, but I guess it shows the potential of this oxybarometer and thermometer for planetary basalts. So I think I'm going to leave here, and thank you for your attention.
Thank you very much. Open for question and comment.
So your vanadium says that your moles are about half a log units above QFM.
Yeah. Yeah.
And on one of the early slides that you showed, based on this vanadium scandium, showed that the moles were about half a unit below.
Yeah, but that's a completely different methodology. Well, vanadium scandium is bulk rock composition, and we are looking at specific partitioning relation between microphenocryst of olivine and melt. Yeah, so they shouldn't be the same.
I was just wondering what your proposed explanation for the difference. Do you think that vanadium scandium simply isn't a good measure?
I don't know. I think we have to do more experiments to look at if there's any different conditions that might affect the partitioning of vanadium and scandium in the sources of subarc mantle and in the below mid-ocean regions. So there might be a difference there that might affect the partitioning.
Okay. So I think we should continue. Thank you very much. So the next presentation is invited, given by Daniela Czerniak. She's talking about diffusion of highly charged cations in olivine.
Well, thank you. I'd like to thank the session organizers for inviting me here today to speak. And I'd also like to acknowledge a few collaborators in these projects, including Bruce Watson, Yan Lang, Jay Thomas, and Jim Van Orman. Okay, today I'll be talking about diffusion of several, or a few cations in olivine. We'll talk about tungsten, phosphorus, and titanium diffusion. This will be, I'll show a few here, some applications of these results from things like hafnium tungsten chronometry with planetary formation, phosphorus fine scale zoning in olivine as a tracer of magma chamber processes, and abundances and distributions of titanium as a fingerprint of magmatic and subsolidus processes. But I really won't be talking today much about applications given the time constraints, and I'll be largely talking about the experiments, some implications from these experiments, where we're heading next with the experiments to better understand what's going on, and finally compare it with and put it in context with some other diffusion data. So first I'll talk about the tungsten diffusion experiments. The sources for these experiments were magnesium tungstate, and it was diluted with some either synthetic olivine or or forsterite or a natural olivine. And these source materials were pre-fired before the experiments. The samples we used both natural olivines from San Carlos, about FO90, and synthetic forsterite. And experiments were run under buffer conditions using nickel oxide or iron wustite buffers. And these experiments were run in 1 atmosphere furnaces using silica capsules, which were sealed under vacuum containing the sample source and a buffer capsule. So there was communication between the buffer and the sample. And there was just indication of the time temperature conditions. We ran experiments at from 1050 to 1450, from 45 minutes to about a month and a half. And the samples were analyzed for the tungsten profiles using Rutherford backscattering spectrometry. So there are some example depth profiles for the tungsten. These are just some examples. The top figures are the tungsten profiles. The bottom figures are inversion through the error function. Because of the source sample configuration, these were very simple. One-dimensional diffusion was an infinite reservoir of tungsten, which was not depleted during the experiments. So you get a simple complementary error function solution, which is what these show. And the slope of the line in the bottom, the inversion through the error function gives the diffusivity. So there's some Arrhenius relations for the tungsten diffusion, showing both the natural olivine and the forsterite. You can see we have diffusion in a couple different directions, parallel to C and parallel to B. B is perhaps a little bit slower, but pretty similar. And we also get very similar results for the forsterite and the natural olivine. And also doesn't seem to be very sensitive to the oxygen fugacity of the system, so we get very similar results for the iron wustite and the nickel-nickel oxide buffer. And the figure on the right, shows a time series. So we ran experiments at varying times at a constant temperature of 1250. And these show, again, similarity between the results for the San Carlos, natural olivine, and the synthetic forsterite, and pretty constant time, diffusivities over a range of times, differing by about an order of magnitude. And on the bottom is the Arrhenius relation down in the corner, showing an activation energy of 365 kilojoules per mole. So here's where we stand with our observations from these results. We see little anisotropy, at least in diffusion parallel to B and parallel to C. Similar diffusivities also for the synthetic forsterite and the natural olivine. And we also see little apparent dependence on oxygen fugacity. We're doing some further experiments to try to explore the substitutional mechanism. Don't quite understand that yet. And also exploration of tungsten diffusion and pyroxene, for which tungsten is more compatible and will help us to better understand planetary problems that we'd like to look at. Okay. So on to phosphorus diffusion. In this case, we use the source of aluminum phosphate plus olivine. Again, the phosphate source was diluted with in this case, natural olivine, because we ran only so far experiments on a natural olivine, again from San Carlos. And we use the aluminum because there's a possibility of having a couple substitution of aluminum and phosphorus substituting in for charge balance. And these experiments were run with a nickel-nickel oxide buffer, and again in sealed silica capsules, sealed under vacuum. And these experimental conditions were quite a bit lower temperature than the ones for the tungsten, and times ranging from 3 days to about a little over 2 months, again in 1 atmosphere furnaces. And in this case, the samples were analyzed by two methods, Rutherford backscattering again, and also nuclear reaction analysis using an alpha P reaction, so an alpha particle inducing a reaction with phosphorus 31 and producing a proton and sulfur 34. And this reaction, we used the resonance of the reaction with an initial alpha particle energy of about 3.65 million electron volts. So here's a profile of the phosphorus. So here you can see a comparison between the RBS results and the NRA results. So we have good agreement with the two methods, and also what looks like good diffusion behavior that we can model. And here's an Arrhenius relation for the diffusion of phosphorus. Again, we have two diffusion directions, parallel to B and parallel to C. And here again, as with the tungsten, we see very little difference, very little anisotropy. And at the bottom is an Arrhenius relation, lower activation energy for diffusion for phosphorus. So as noted in the previous slide, we see little evidence of anisotropy. These experiments we're planning to run in the future include experiments on synthetic forsterite and also investigating the dependence on oxygen fugacity. And we're also concerned about trying to characterize the substitutional mechanism for phosphorus into the samples. We have some preliminary results for aluminum profiling in these samples with the aluminum phosphate source, and they seem to indicate much lower aluminum concentrations than phosphorus, so we're not quite sure what's going on there. These, again, results are preliminary, so we're still trying to understand them. And we're considering other sources of diffusion to better understand what possible charge balances could occur. For the titanium diffusion, here we used basically a titanium-doped olivine, substituting part of the silicon for titanium. And this, again, was diluted with either a synthetic forsterite or a natural olivine, depending on the samples we used in the experiments. And again, here we used natural olivines, again, from San Carlos, and also the synthetic forsterite. These experiments were either run in platinum capsules and air, in the case of the forsterite, or they were run under buffer conditions in the sealed silica capsules, as the previous experiments I talked about. And again, at nickel-nickel oxide and iron wustite buffers. And there's the experimental conditions, so 895 to 1400 degrees, 30 minutes to nearly 3 months in 1 atmosphere furnaces. And as with the tungsten, we profiled our titanium in these samples with Rutherford backscattering. So here's an example of some of the titanium profiles. Again, this is an infinite source of titanium, so we can model with the complementary error function solution. So just an example of a couple of the profiles and the inversion through the error function. So for titanium diffusion and forsterite, on the left, you can see we have, again, the two different directions, a little evidence of anisotropy for diffusion parallel to B and parallel to C. And on the other figure, you can see we showed the titanium diffusion parallel to C with both the San Carlos and the synthetic forsterite. And again, we see similar results. And also pretty consistent behavior at constant temperature over a range of times. And here we have the Arrhenius relation on the bottom, and we have a lower activation energy for diffusion than either the tungsten or the phosphorus. So as noted, we see little anisotropy and similar diffusivities for the synthetic forsterite and natural olivine. and little apparent dependence on oxygen fugacity. The titanium diffusion, and also we place this in context with some earlier data on titanium diffusion in pyroxenes that we've published this year, and titanium diffusion is faster in olivine than in pyroxene at temperatures below about 1050. And then we're doing some experiments now to better explore the substitutional mechanisms, considering the presence of hydrous species, for example, the substitution of the titanium on M sites in the presence of them, as Barry et al. Noted. So before I go on to talk a little bit about these data in context, one thing that's been discussed in the literature is the issue of surface preparation and how that affects diffusion. So typically our samples are polished in the procedure that you see there, and we've done some work with FIB and SEM to look at the surfaces to see whether this kind of polishing procedure does produce any extended defects or damage deep into the surface that may be comparable to the lengths of our diffusion profiles. And the data we have suggests that we have very nice surfaces on a very small scale, so this indicates that our profiles are definitely in range where we don't have significant amounts of damage in the material. So I'll just show some selected data for cation diffusion in olivine. On the left, the sources of data are as indicated, and on the right, we have some other data, including some data from the elements that we're looking at. We have pretty good agreement with the Mormont et al. Results, and some disagreement with some of the other data, which we do not fully understand yet. So just some possible reasons for the differences, differences in analytical approaches, although it seems unlikely given good agreement with the Spandler et al. And O'Neill et al. Results with other diffusion of other cations, and our results agreement with other studies using SIMS and electron microprobe with other elements that we've studied. And then possibly different compositional effects or potential differences in substitutional mechanisms, cracks, subgrain boundaries, other fast transport paths are a possibility, as well as dissolution and precipitation, particularly in studies from natural samples. So just to summarize the results that we presented here, so we see that faster diffusion of phosphorus compared with titanium, compared with tungsten under most geologic conditions. The diffusivities of these high charge elements are relatively slow, and thus far we see little dependence on FO2 orientation or composition under the investigated conditions. And the reasons for the difference in diffusivities of some elements in olivine among different studies are still unclear. Thank you.
Thank you, Daniele. So it's time for one quick question, maybe, or two. Yeah. Yeah, yes, please.
Sorry for this, but how much tungsten you were able to get into olivine?
We're seeing on these experiments up to a couple hundred ppm. So, but it's not a natural system, obviously.
So, any more questions? Okay. Thank you. Then we move on to the next presentation, given by Zio and co-authors, and talks about telling zone from zoned, laser ablation, multi-collector ICPMS and SIMS, SIMS iron isotopic measurements of olivine. Thank you.
Thank you.
So.
All right. Thank you for staying for the talk. Today I'll be talking about olivines from an isotopic point of view, particularly how stable isotopes could be used to understand nature of zoning in olivine. And chemical zoning in olivine are very common. They're seen in Martian meteorites, chondrules, and terrestrial basalts. However, most of the time, we don't really understand how these olivines became zoned. And that's because zoning can be produced by two mechanisms, and they could be occurring at the same time, but here I'll be discussing the end members of them. So to start, we look at the KD value of olivine. It's at about a constant ratio of 0.3 over magmatic temperatures, which means that magnesium is compatible in the olivine. So in the first scenario, where chemical zoning is produced by crystal growth, we consider that initially an olivine is in equilibrium with the melt, and as time progresses, more olivines are growing from the melt, driving the melt composition to become more iron-rich. And at the same time that the melt composition is evolving to more iron-rich composition, the overgrowth layers around the olivine is also becoming more iron-rich in order to stay in equilibrium. In the second scenario, where chemical zoning is produced by diffusion, we also have new olivines growing in the melt that drives the melt composition to become more iron-rich. But instead of having overgrowths, we have iron diffusing into that initial olivine crystal to equilibrate. And in the first case, if zoning is produced by crystal growth, there's little thermal history information from this grain because besides the fact that it did not stay at high temperature long enough to flatten out the zoning profiles. Then, however, in the second case, if the chemical zoning are actually diffusion profiles, we can model the thermal history of the system because diffusion is dependent on time and temperature. And given that the two types of zoning, they give you very different information, but they can look very similar, then how do we distinguish between the two of them? In an earlier paper, we proposed that we can use stable isotopes to tease apart the two. But for the first time, we'll show definitive evidence that this is the case by showing you spatially resolved data. And this is how it works in crystal growth. We know the iron isotopic composition of the olivine is approximately equal to that of the melt. So as the olivine growing, each overgrowth layer is in isotopic composition with the surrounding melt. If we make an isotopic profile from the core to the rim, we would see chemical zoning, but there is no isotopic zoning. In the second case, that diffusion controls the chemical zoning in olivine, we know that light isotopes always diffuse faster than the heavier counterpart. So at a given time, iron 54 would have diffused to the center of the olivine before iron 56 can. And if we make a chemical profile from the core to rim, we would see an isotopically light iron isotopic signature towards the core because it is enriched in iron 54. And at the rim, it will be isotopically heavy because it's enriched in iron 56. When iron is diffusing into the olivine crystal, magnesium has to diffuse out. And the same story goes for magnesium isotopes. Magnesium 24 would have reached the rim of the crystal before magnesium 26 can. And what we see here, it's a negatively coupled profile between the magnesium and the iron isotopes, and they're negatively coupled because magnesium and iron are diffusing in opposite directions. So having this idea in mind, we searched for a sample to work with, and our sample comes from Kiroiki lava lake from Hawaii, and shown in the picture here is a picture of the lava lake. It's formed in 1959 by magma inflow into a pre-existing crater. And shown here is a cross-section of the lava lake, and this red point shows the location of our sample. And the nice thing about this locality is that the cooling timescale is actually observed. It is exactly between the time of eruption and when our sample was quenched by core drilling, and that time scale is 21.4 years. And this is the olivine that we worked with. It's zoned from FO65 to FO85, and we have done micro drilling analyses across a vertical and a horizontal profile. The powder, micro-drilled powder, were dissolved and purified for magnesium and iron isotopic analyses by MC-ICPMS, and shown on the right panels are the results of those analyses. Here, it's the red are the isotopic profiles for magnesium, and the blue are the isotopic profiles for iron. We see that, as expected, if diffusion controls the chemical zoning, these isotopic profiles are negatively correlated. The fractionation for magnesium is about 0.3 per mil, and that for iron is about 1.2 per mil. And the drill bit size that I had used for this technique, it's about 300 microns, which is bigger than many zoned olivines. So we went on to developing techniques that can provide much higher spatial resolution. And we had done it for iron isotopes, but we bear in mind that the same study could be done for magnesium isotopes also. And the techniques that we have developed, it's laser ablation, MC-ICPMS, using a UP193 excimer laser. And for the other technique, it's a SIMS, a 1280 SIMS at CRPG Nancy. Both of these techniques give spatial resolutions about 50 microns in diameter. We've done a lot of work to ensure the accuracy of data, but here I'll just show you the results. And the picture here shows where the traverses were taken for the laser, SIMS, and the micro drilling. They're all plotted on the same vertical scale. So we can see that in all of these profiles, the iron is isotopically light at the center. And the fractionation, it's about 1.3 per mil to 1.2 per mil. And here I show you the vertical profiles. They also compare very well with one another. But comparing the three techniques by versus distance, it's not the best way to look at it because the profiles were not taken immediately adjacent to one another. But we know that the FO number of each analysis spots were functions of distance. So we can actually compare the three techniques better if we make a plot of delta 56 iron as a function of FO number. And in this plot, we can see that there is very, very good agreement between the three techniques, which demonstrate that we can obtain accurate data by using laser ablation and SIMS. And we ran a diffusion model through the data point, and it became apparent to us that only the steeply sloping part could be modeled as diffusion controlled. For compositions that are more iron-rich than FO80, the isotopic values are relatively similar, and which means that this region, it's not controlled by diffusion. And we interpret this region as a late-stage overgrowth of the olivine. And we actually have petrographic evidence that this may actually be the case. In other drill cores from the same lava lake, the average olivine rim number, it's always around FO80, as seen in other drill cores. So this Fe-rich region on our samples, it's actually anomalous. And another important observation is that 3 weeks prior to when our sample was retrieved, there were other drilling activities that took place just 8 meters away from our drill core. And these observations together suggest that the nearby drilling activities had perturbed the temperature field of our sample, driving the late-stage overgrowth for this anomalously high iron content region. And you can actually see the overgrowth around the rims of the olivine, and you can see the olivines growing into the ground mass material. So here we show the virtue of using stable isotopes on the zoned olivine study, because chemically the overgrowth could not have been distinguished from the region that is controlled, from the chemical zoning that's controlled by diffusion. So for the diffusion model, we have excluded the overgrowth part, and here I go into a little bit detail for the modeling parameters. For the diffusion equation, we had used the equation from Dolman and Chakraborty 2007, and we measured the crystallographic orientation of the olivine because MGFE diffusion in olivine is strongly anisotropic, and the FO2 is taken to be at the NNO buffer, and the lava lake is hydrated, so we multiply a factor of 4 to the D to account for the presence of water. And this factor of 4 is actually within the uncertainty quoted by Dolman and Chakraborty. And for the cooling function, we had used a conductive cooling regime because it is a generally good assumption for igneous body, and it had been shown to work well for several lava lakes. And for boundary conditions, luckily this lava lake has been really well studied, that it's really well constrained from petrographic studies and also from laboratory experiments. The equilibrium olivine number, it drops linearly with falling temperatures. And the last parameter that we need is this beta exponent that relates the diffusivities of the isotope to their masses. In this study, it will be a fit to the data, but beta can actually be precisely determined in laboratory experiments, and that's what we're working on. If beta it's known, then it can actually provide some clues for the boundary conditions for systems that are less well known. For the modeling results, I show you two curves. The red one represents the diffusion model run for a beta value of 0.24, and the black curve shows the model run with the beta value of 0.32. And again, these provides pretty good estimate for the beta value, but we're trying to determine precisely this value in laboratory diffusion experiments. And if I collapsed all of the profiles into their respective, all the vertical and horizontal profile into their respective common distance axes, you can see that the diffusion profiles can describe the isotopic profiles very well. And because, as I said, the profiles were not taken immediately adjacent to one another, so I can only show you the approximate area of where the overgrowths are. And there is still a region for the horizontal profile that needs explanation. It's relatively flat. And if we look at the chemical profile across these regions, the horizontal traverse, we can see that actually two chemical profiles were joined together. And this very likely represents crystal attachment of a smaller crystal attached to a bigger crystal. And these type of crystal attachment, it has been documented to happen very frequently, to occur very frequently in the same lava lake that we have studied. And they were documented in the eruption samples. So our diffusion model can reproduce the observed timescale of 21.4 years. So our diffusion model works very well because of the many constraints that we have from the iron isotope studies. And in conclusion, the take-home point is that the in situ stable isotope measurements, they're a critical tool for studying zoned mineral. And we have used olivine as an example, but such studies can be also applied to other commonly zoned minerals in igneous and metamorphic rocks. And the thermal history can be obtained if we know which zoning is diffusion control and which are, it can be distinguished from crystal growth. And lastly, this type of study provide information on diffusive transport at the atomic scale. It provided the beta for iron and olivine to be about 0.3 and beta for magnesium is about 0.2. So thank you for your time.
Thank you very much. We have time for 2 or 3 questions. Yes, please, Glenn.
It would seem to me that you could get additional information by looking at minor elements that have very different diffusivities from iron magnesium, like calcium or tungsten and titanium that Danielle showed. That they'll behave differently during growth from during diffusion.
Right. So we did analyze the minor elements for calcium, aluminum, that's chromium, and nickel. I mean, we made plots of these minor element concentrations, function of FO number, and it was suggested that you may be able to see a kink in these trends, and that would be indicative of zoning that is not purely diffusive or growth. But here, we made a similar plot, and I have highlighted the region that represents the overgrowth. And for chromium, aluminum, and nickel, these trends could not have distinguished the overgrowth part from the diffusion-controlled regime. And for calcium, you see a change in the trend, but it can be also purely due to crystal growth or purely due to diffusion, because the incoming of plagioclase and algae takes in calcium, and what you have, it's a depletion in calcium in the melt when algae and plagioclase crystallize. So this could have happened around FO80. And in another case, it could have happened, the boundary condition could have changed according to the crystallization of algae and plagioclase. So you have a boundary condition that is increasing in calcium content with time. And when plagioclase and algae crystallize, you have a decrease in the concentration in the calcium. So that change in the boundary condition in the calcium could give you the same trend. So it's not unambiguous by minor element.
Any more questions? Maybe just one general question for me. So you mentioned that if it's growth, then you wouldn't expect any isotopic fractionation. But if it's a diffusion-controlled growth, then you would have a diffusion boundary layer in the melt that would produce maybe also a certain isotopic fractionation pattern. Is that, yeah?
So
how can you distinguish these 2 cases?
So you're talking about diffusion limited growth?
Yes, exactly.
Okay.
Yeah.
So the question was diffusion limited growth. What if you have your diffusion limited in the melt? And that would actually give you positive correlation between the magnesium and iron isotopes, because they are diffusing in the same direction, and the KD value for iron, it's actually larger than 1, and for magnesium, it's larger than 5. So they are diffusing in the same direction, and yeah, they would not be negatively correlated. Yeah.
Okay, thank you.
Okay, thank you.
Okay, I think that was the final talk of this presentation. Thank you everyone for attending this session.